One of the most important things that we need to recognize whenever we're studying algebra is when we're looking at two algebraic structures that, while on the surface they might look different, they're actually identical. We've been talking about this for most of the course, and we talked about this in terms of two groups being isomorphic. Not that they're the same exactly, but that their structures are identical. Their underlying algebraic structures are identical. We began looking at this by means of Cayley graphs, showing that two groups are isomorphic if they can both be represented by the same Cayley graph. And then much more recently, we looked at this idea in terms of the notion of an isomorphism, a bijective function which preserved the operation from one group to another. In your last homework assignment, one of the things I asked you to do was kind of a silly exercise. I asked you to show that a group was isomorphic to itself. Well, of course a group is isomorphic to itself, isn't it? It can be represented by the same Cayley graph that it can be represented by. If we use our old definition, this is trivial. But I asked you to do it in a different way. I asked you to use our new notion of showing that there was an isomorphism that existed from a group to itself in order to prove this result. What I've done here is to show you how I approached that problem. What I did was to take a group G, and let's go ahead and take the most simple function that we can imagine on this group, the function that sends an element to itself, the identity mapping, right? We're going to show that this is in fact an isomorphism. I think it's clear that it's bijective. Certainly it's one-to-one, certainly it's onto. No problems there. But also it's easy to show that F preserves the operation, right? The second part of the definition of isomorphism. And here's why, right? If I take the product of X and Y, well, F takes everything to itself, so it's going to take that product to itself. But X is the image of X, and Y is the image of Y under F. And so we have that F of X star Y is the same as F of X star F of Y. And so, yeah, the identity mapping is in fact operation preserving as well as bijective. So it's an isomorphism, right? An isomorphism from a group to itself is what we are going to call an automorphism, and it's the subject of this video. The fact that we even have such a definition suggests that probably the identity mapping is not the only automorphism from a group to itself in general. It might be in some cases, but there are certainly many groups that admit automorphisms that are different from the identity mapping. One of those I asked you to do also for homework last time. I asked you to find an automorphism. We didn't call it that then. I asked you to find an isomorphism from Z4 to itself that was different from the identity mapping. The one I've picked is the one that interchanges the numbers 1 and 3. So let's let F be the function that sends 0 to itself, sends 1 to 3, sends 3 to 1, and sends 2 to itself. Well, what I've done is I've drawn a couple of Cayley graphs that illustrate Z4, that represent Z4. The first one over here is the traditional one, right? The one that I'm using an arrow to mean add 1. So 0 plus 1 is 1, add 1 again, I get 2, add 1 again, I get 3, add 1 again, I get 0 in our mod 4 addition. But under the function that interchanges 1 and 3, right, so here it is. So in place of 1 over here, I've written 3. In place of 3, I've written 1. Now my arrow means add 3. It's still mod 4 addition, right? But 0 plus 3 is 3. 3 plus 3, let's see. In ordinary addition, that would be 6. In mod 4 addition, that's 2. If I add 3 to 2, I get 5 in ordinary arithmetic, but 1 in mod 4. And if I add 3 to 1, well, in mod 4 arithmetic, I get 0. Right? So this function also, this function serves to preserve the operation, preserves mod 4 arithmetic on Z4. And so, in fact, F is an isomorphism from Z4 to itself. F is an automorphism. I want you to observe that if F is an automorphism, then, well, right away, F is one-to-one and onto. Why? Well, F, it's an isomorphism, and isomorphisms are bijective, right? Isomorphisms are bijective by definition. And so any automorphism is going to be a bijection. What that means is that it's a permutation of the elements of G, right? It's a bijection from G to itself. Well, that's exactly the definition of a permutation of the elements of G. It's going to rearrange the elements of G. But if I looked at all of the permutations of G, we've looked at that set extensively in the recent past, right? In fact, we even gave a name to it, right? S sub G, it's the set of all symmetries of the elements of G. And so if F is an automorphism of G, then F belongs to this known group that we, and of course the group is with respect to the operation of composition. So this collection of automorphisms is a subset of this group of permutations. What we'd like to do is show that the set of all automorphisms of a group G forms a group on its own, right? We already have that all of these automorphisms belong to our permutation group. I'd like to show that all of those automorphisms actually form a group, right? And so since all automorphisms of G, and I'm going to abbreviate that with this notation, auth G, the set of all automorphisms of G, since they all belong to S sub G, well, that means initially that this set is a subset of this permutation group. And so we can prove that the collection of automorphisms of G is a group by showing that, all right, do you remember how this is done? If we have a known group and a subset of that group, we can show that that subset is a group by showing that the subset itself is a subgroup of that known group. And that's what we're going to do. This is handy because it eliminates a lot of different checks. We don't have to, whenever we know that we have a subset of a known group, we don't have to show that all of the group axioms are satisfied. There's a shortcut, there's a characterization for subgroups that we're going to be able to use that's going to be very handy. So we can show that this subset is a subgroup by showing, let's see, first of all, that that subset is closed under the operation, and the operation on the set of permutations of G is composition, and also that that subset is closed with respect to inverses. If we can show those two things, as you'll recall, that will show that this subset of S sub G is actually a subgroup of S sub G. So how are we going to do that? Well, let's start with the first condition. Let's show that the collection of automorphisms is closed under composition. Remember what that means, right? It means if I reach into the collection of automorphisms and pull two of them out, that their composition is also going to be in this set. Well, let's go ahead and let's do that. Let's take two members of the automorphism set of G and notice first of all, so we have to show two things, right? We want to show that f of G is an automorphism. So we're going to have to show f of G is bijective. We're going to have to show that f of G preserves the operation on G. Well, since f and G themselves are bijective, we already know that their composition is going to be bijective. We've shown that. We showed that a long time ago, that the composition of bijective functions is bijective. So that part's done. That part of the definition of isomorphism is already taken care of. All we have left to do is to show that f of G preserves the operation on G. So we'll do that by taking a couple of elements out of G and multiplying them together and see what f of G does to that product. Well, okay, so by definition, f of G, well, it's going to do this to that product by definition of function composition. So it's going to look at what G does to the product, and then it's going to look what f does to that result. But we know that G, right, we're assuming that G is an automorphism. So G preserves the operation on the group G. So I'm going to be able to write G of x star y as, do you have it? G of x star G of y. Right, so this follows because G itself is an isomorphism, but f is also an isomorphism. And so I'm going to be able to write this expression as f of G of x star f of G of y. Well, that's exactly what we wanted to do, because this is the definition of f of G of x, and this is the definition of f of G of y. And so we have that the composition f of G takes x star y to f of x, f of G of x star f of G of y. The composition preserves the operation. Right, and so since f of G is operation preserving and it's also bijective, well, that's the definition of an isomorphism, right? And since it's an isomorphism from G to itself, it's an automorphism of G. So if I take any two automorphisms out, compose them together, I get another automorphism. So the set of automorphisms is closed under composition. So if we happen to be working in a finite group right now, well, if the group is finite, then the number of permutations on that group would be finite as well. This would have been enough to show that the automorphisms form a subgroup. I don't want to assume that G is finite, therefore I don't want to assume that the collection of permutations on G is finite. So I'm going to go one step further and show that the set of automorphisms is also closed under inverses. Now remember what that means. If I have a box of automorphisms of G and I identify one of them in that box, then whatever I pick out, I can also find its inverse in that box. That's what it means to be closed under inverses. So I'm going to take an automorphism out of that box, and notice first of all that since it's a permutation of G, and G's a group, and the permutations of G form a group, we know that F has an inverse, right? And we also know how that inverse is defined, right? The inverse is going to be the function that undoes what F did, right? In other words, F inverse of B is going to be the element of G that F sent to B in the first place, right? So if F sends A to B, F inverse is going to send B back to A. That's the definition of F inverse. Well, to start with, since we know that the inverse of a permutation is also a permutation, we have from our work earlier that F inverse is bijective. So that part of the definition of isomorphism is already satisfied. We just have to show that F inverse preserves the operation on G. So toward that end, let's pick a couple of elements out of G. Right? We're going to have to show that F inverse of x star y is F inverse x star F inverse y. But let's get ourselves up to use this definition up here of the inverse by letting A and B be members of G that so A is the member of G that F sent to X, and let's let B be the member of G that F sent to Y. In other words, F inverse of X is A, F inverse of Y is B. Right, so let's use that and notice that, well, let's see, on A and B, F being an isomorphism, F preserves the operation on G, so F's going to send A star B to FA star FB. But what does that mean? Well, F of A is X, right? That's how we chose A. F of B is Y. That's how we chose B. And so we have that F of A star B is X star Y. Well, by the definition of F inverse, what that means is that F inverse of X star Y is A star B. Right? That's exactly what this means by the definition of F inverse. F inverse of X star Y is A star B. But A, where is it? There it is. A is F inverse of X. B is F inverse of Y. So A star B is F inverse of X star F inverse of Y. And that finishes the proof for us, right? So we have that F inverse of X star Y is the product of F inverse of X and F inverse of Y. F inverse preserves the operation. It's also bijective, so that makes F inverse an isomorphism from G to G, therefore an automorphism. So if I pick a F out of the set of automorphisms, I know that F inverse is in that box also. The automorphisms are closed under inverses. So, in conclusion, what we've shown is that since the automorphisms form a subset of this known group, the group of permutations on G, and this set is closed under inverses and also under the operation of composition, that shows us that this collection of automorphisms is in fact a subgroup of the permutations of G. So the automorphisms under composition form a group. I have a couple of things I'd like you to do for homework. First of all, I want you to show that if you have three groups, we'll call them G, H, and K, and G and H are isomorphic, so there's an isomorphism between G and H and K are isomorphic, so there's an isomorphism between H and K, that the composition, G of F, turns out to be an isomorphism from G to K. Now that appears as Theorem 176 in your notes. I'd like you to prove that. I think you'll be able to, this is actually an extension of some of the work we've done in this video. In this video, we were working only with G, G, and G. Now we're working with three different groups, G, H, and K. And we're going to show that the composition is in fact an isomorphism. What that will show is, well, let's see, as a consequence, it shows that if G is isomorphic to H and H is isomorphic to K, then G is isomorphic to K. So that'll be a formal proof of that. I'd also like you to show that if I've got an isomorphism between two groups, then the inverse function, the one that undoes what F does, defined in this way, also turns out to be an isomorphism. So a consequence of that would be that if G is isomorphic to H, then H is isomorphic to G. If you'll do those two things for homework, I'll do them as well, and we'll compare answers the next time we're together. That's our discussion on automorphisms. I look forward to seeing you next time. Until then, stay well, stay safe. I'll see you then.